Hi. So today let's discuss some interesting problems where we usually use some logics for the proofs in some propositions that we normally see. Okay. So, but we want to ask that how can we actually use the logic to help us to prove the things, right? So today we're gonna discuss some of those very fundamental logics for us to use to prove some propositions that we see or that we construct. Okay, good. So when we say we're talking about a proposition, it could be either true or false. Okay, it cannot be both true and false. Okay, it has to be either true or false. So, but we're not gonna define what is a proposition. You can just think it as some statement or some arguments, right? Okay, so let's say, let's suppose P and Q, there are two propositions, okay? So here we have some notations, okay? So where we have this P, so it's just the negation of P, so that is just not P, okay? And this is P and Q, okay? We're not talking about the formal definitions. It's just the how do we read those notations, okay? And this would be the P or Q, okay? And this would be the P implies Q, or we can say that we can read this also as if P then Q, right? Those are just the normal, the common logic that we read from those notations, right? And this can be read as P only if Q, right? Or just Q implies P on the other way around, right? And the last one would be just equivalent. So P is equivalent to Q. Sometimes we can also write 3 lines to indicate the equivalency. Okay, so those are the same thing. So when we're talking about the equivalence here, so we need to match all the possible values for all different combinations of the cases that we have. So what do we mean by all the combinations of the possible values or the truth values for those arguments or for those propositions? So next we're gonna introduce the truth table. That is a very powerful tool for us to use to construct the proof or the argument that we or the construct the logics that can be used for our proofs. Okay. And normally when we might have heard a lot of proofs using either contrapositives or using the contra or using the contradiction, right? So all of those proof skills, they are just some specific or some special cases of those approaches that we can discover in the truth tables, right? So you can just essentially build your own proof by using a truth table, okay? And as long as you can match all those cases, then it will work, okay? Good. So next, we're gonna see what is this truth table, okay? So here we have this as our head of this table, okay? So that would be the header of this table, okay? So we have those, each one of those argument or one of those proposition is taking one column, okay? So for example, we're gonna fill in all the possible cases, okay? So let's start with the P and Q, okay? So to exhaust all the possible combinations, we put, okay, let's change the pen here. So we put 2 for P. So it can be true or false, okay? And combined with Q, so this should exhaust all the possible combinations between P and Q. So this can be F, and this can be T and can be F, okay? So this is given, okay? Now next, we're gonna use this table and use the logics that we just defined, using those operators And by the definitions of all those operators, although we didn't mention the exact definition, but we know we can just use the interpretations of those logics to get those results. Okay, good. So then immediately we know that P and Q, this has to be true, right? And P and F, this has to be false because we require for both to be true for this P and Q to be true, right? So this is false and this is false. Okay, and P or Q, so as long as we have at least one true, so this can be true, right? And this is false. Okay, so let's have some lines here. Okay, good. So all right, so the negation is just the opposite of that, right? So this would be false, false, true, true. This would be false, true, false, true. Okay. We are given those two columns, and all the others were just derived from those two columns, right? Okay, so when I have the result for P implies Q, okay. All right, so this becomes a little bit interesting. So when we're saying that P implies Q, okay, so if P is true and Q is true, then this is true, okay? So if P is true, Q is false, then this is false, okay? So when we have some true P and we conclude some false Q, then this implies it's false, right? We cannot imply from the true P to have this, to get to a false Q, right? So this operation should be false. Okay, so how about the other one, the other two? So we're gonna assume, or we're gonna simply say that those are true by default. Okay, the reason is that this is not by any logic. So this is just by assumption, or you can take this as given. So the reason why we just take those two as true, this is because that we have all those P in those two cases, we have those P's to be false. Okay, so it means that here, this is by default, our assumption or our condition of this P is false. So we don't have that P. We don't have a true P to be able to say something about Q, right? So this simply means that, okay, well, our original or our previous assumption or our ground condition, it doesn't exist anymore, okay? So in this case, we simply say that if we have P to be false, then in this case, it doesn't matter whether the Q it is true or false, because we do not have a true P anymore as our starting point. Then it doesn't matter whether this Q is true or false. Then we simply give this relation, this imply, to be true. Okay, so this is by default or by assumption, or just this is like defined by the logic. Okay. And this is also intuitive, right? This is not a very strong assumption or strong default, right? We can still understand this. Good. So this is the implies, okay? And then we can also try this, take some exercise for the other column when Q implies P, right? For the next column. Okay, so if Q is true, then P is true, then this is true. Good. If Q is false, okay, be careful. If Q is false, then this is by default is true. And it's same for here, right? And if Q is true and P is false, then this is false. We cannot get from a true thing to a false thing, right? So this is false. Okay, good. So that'll be the P implies Q and Q implies P, right? Okay, so the next would be the equivalency. Okay, so P if and only if Q. Okay, so in this case we have to match so all the possible cases, right? So here we simply need to match the P and Q for all those four cases, right? So that's what we're gonna do here. So if we can match, so literally, right? If we can match those two letters, then we put a T here. If we cannot match, then we put an F. Then we cannot match, then put an F. If we can match, then put a T. Okay? So that's the T, F, F, T. Okay? So that's the if and only if, or the equivalency. Okay? So this is a biconditional. Okay, good. So the next is gonna be this negation of Q. Not Q implies not P. Okay, so that would be the something that we normally see is called the proof by contrapositive or contraposition. Okay, so just simply using the negation of the result and use that to imply the negation of the condition, right? And if this is true, then we say that the P implies Q is true. Okay, so so the thing that we're gonna sort of so-called prove is to prove this thing. Okay, so that's our initial sort of proposition, and the argument or the statement by the contrapositive is this. Okay, so this is the contrapositive. Okay, so and we want to ask a question that why this contrapositive it is equivalent to the original proposition P implies Q, right? So that would be the key question here, and then we're gonna use this truth table to show us that those are essentially equivalent. Okay, and by definition, the equivalence means that for each row here, okay, for each row we have all those values to be the same, okay, to match, then they are equivalent, right? Okay, good. So let's fill this table for this column. Okay, so let's start from this. The first row is that, so this column is saying that if we have a negation of Q, that would be this column, okay? And then that implies the negation of P, so that implies this, okay? So, and remember that whenever we have the condition to be false, then this is automatically true, and the same for this one, okay? And true implies true, of course, is true, and true implies false, this is false, okay? All right, and then we immediately observe something that we can see that this, okay, let's change the pen here. This entry matches this matches this matches this, and this matches this, right? And all of those match correspondingly for each entry, and then we can say that this is equivalent to this. So we can prove something that is the argument of P implies Q that is equivalent to prove its contrapositive or prove its contraposition. That is saying that not Q implies not P. Okay, good. So that's the proof by contrapositive. So the last thing that we're gonna discuss today, that would be the proof by contradiction. Okay, so let's erase those first. Okay, good. So let's fill the last column here. So when we're talking about the contradiction is something saying that we're having this P and not Q. So Q is the result, right? So we're gonna suppose that the result is false, okay, or not false, it's just a negation, maybe false or true, right? We're gonna suppose that the negation of the result, and then also we're gonna have we're given the condition, okay, and this is the end. So we have those two things at the same time, and this implies the condition is the negation of the condition. So then this contradiction means that we have this condition here assumed, but we result in a negation of the condition, right? So that would be that would mean the meaning of the contradiction. Okay, good. So let's fill in this truth table for this column. Okay, so let's find out all those parts that we're gonna need. for this column. So P is somewhere here, and let's erase those arrow. Okay. And the negation of Q, here we should use the lowercase q, right? It's not capital, but you know that. Okay, so the negation of Q, that'll be this, right? And negation of P, that'll be this. Okay, good. So I think we're gonna need something, right? So we're gonna do this P and negation of Q first, right? So let's move this a little bit to the right, and let's do the P and negation Q first. Okay, let's just use the lowercase q. Okay, so that'll be helpful for us to take this first, right? So let's have P and negation of Q, right? So this is T, this is F, that'll be F. And T, that'll be T, F and F, that is F, F and T, that'll be F, right? Only T and T, that gives T, right? Let's double check. TF gives F, and TT gives T, FF gives F, FT gives F. Okay, good. And then we're gonna use this column and this column, those two circle columns, okay? And we wanna imply from this one, from P and negation Q, and to get the negation of P, okay? So, and remember that when we are having the conditions to be false, 1, 2, 3, that's good. That saves a lot of work, right? So whenever we have the condition to be false, then this is immediately true, because this is by default. Okay, there's not so much logic. It's just by intuition, right? So we do not have any conditions here. So it's just this implies it is automatically true. Okay, and then let's check the other one. So if this is T, and it's saying that this is F, so that would be F. Okay, good. So let's verify our result. So here we got this T, and we're gonna show this will be equivalent to this, right? And F, F, T, T, T. Okay, so this is working, right? Awesome. So now we successfully showed the equivalency between the original proposition P implies Q and those two equivalent ones. The first one was the contrapositive or the contraposition, the same thing, and the second one using the contradiction. So if you can construct by yourself, construct any of those, like, because those two approaches, they're just sometimes if it is not quite easy for us to prove the original statement, right? So people just to use those two alternative ways to prove. It's just some ways, right? Some approaches. You can always come up with your own approaches or own ways, just using this interesting truth table, right? Just based on the very fundamental the conditions and the result that given initially. Then you can build any of those, maybe simple or maybe complicated, as long as it can be used to prove the things that you're gonna need to prove, right? And you can at the end of the day, you're gonna show that your proof logic will be essentially equivalent to something that you might need to prove, that maybe P implies Q, or something later you might need for Q implies P, right? Or the equivalency for the proof, right? Okay, so that'll be really helpful for us to understand and even to construct our own proofs in the future studies, right? Okay,